Are there any questions?
No, sir.
What does he say?
So that's the title. I will change it.
Joseph? Joseph?
Sir?
Is Satya not coming?
Just a minute, sir. I will call him. Just a
Yeah,
minute, sir.
yeah.
He's supposed to come. Soon, sir. I call him.
Ah.
Another minute, he will come, sir.
Okay. So maybe in another minute we can start, right?
Yeah, yeah. Now 9:59, so we can wait for one more minute.
One more minute, yeah. Meanwhile, if there are any questions, please ask.
Yes, sir.
Good morning, sir.
Good morning.
Sir, this is Ritesh, and I'm trying to work on some particle physics experiments, sir.
Okay.
And I was reading your notes last week, sir.
Yes.
Satya sir forwarded the notes.
Yes.
Sir, I want to know a book to learn about all these lectures, sir. Some a reference book.
I have already given a list of books in the beginning.
Yeah, yes, sir. But in
On the
that
first.
if you can say one book as a beginner, if you have to choose one book, what you will say, sir? The best book to start with.
I have already given them, but anyway, let me give. Perkins.
I have the list of books.
Perkins is one book.
I need a suggestion, just one book. Only one book if you will suggest me.
In that case,
Perkins.
Perkins is good, but there's a better book. I forget his name.
Thank you, sir.
No, you should look at 2 or 3 books, and you should choose the book which suits you. Griffiths.
I was going through Harrison and Martin, sir. Harrison and Martin.
Yeah, that is more advanced. That is more theoretical and more advanced. Okay, but it's okay. That also we can look at. But I would suggest that Griffiths you should look at. Griffiths. Okay, this is better, and this is more experimental based, so it is easier to understand. And Halson, right? Halson and Martin, more theory based. This is more experiment based, and it's more theory based. So I would suggest that you start with this. Okay, you look at all the 3 books and choose which is best for you. You can come back to the other books later. All right?
Okay, sir. Okay, sir.
Yeah. Joseph, shall I start?
Yes, sir. Yes, sir. Yes, sir.
Okay. So I am starting my lecture 11. I want to know, Joseph, I have forgotten. Last lecture 10, did I talk about the discovery of neutrino mass?
Just a minute, sir. I'll.
Please check. Otherwise, I will do it again.
Satya, sir.
Satya has not.
Yeah. Hello. Sir, sorry, sir.
No, it's okay. Satya, did I do discovery of neutrino mass last time?
Yes.
I have done it, right?
Yeah.
Talking about how the discovery took place and the mass square differences and so on, and the Majorana nature of the neutrino, all that I have talked about, right?
Then towards the end.
Yeah, towards the end I talked about it, right?
Yeah.
In that case, let me. So today let me talk about gauge theory. Lecture 11. Hereafter I will give the title of the whole lectures. All the topics which I am going to cover I will mention here. First, a repeat of whatever I mentioned earlier, the relativistic notation and so on. This is a repeat. So we denote the space-time vector as x mu, which is equal to x0, which is t, ct, but c equal to 1, and xi, 1, 2, 3, the 3-dimensional vector denoting the position, and this is the time at which the particle is observed. And This is called contravariant vector, and the covariant vector. Hello? Yeah. Yeah. The covariant vector is simply the same, except that x0 remains the same, but xi becomes minus. Can be obtained formally as g mu nu x nu, where g mu nu is 1. It's basically a unit matrix, but with some minus sign for the spatial components. Okay, that is contravariant covariant. And Lorentz transformations are those which take x mu to x mu prime. If there is a frame of reference moving with a velocity v, you know how to write it. I am sure people who have started learning special theory relativity would have seen how that x minus vt divided by root of 1 minus v squared by c squared comes, right? And I will not write that explicit form, but I will write it more generally. A mu nu x nu. Of course, repeated indices are always summed over. These are constant matrices, I mean constant numbers, so it is a constant matrix, and A mu nu is such that the so called invariant length, space time length, x mu, remember one is above, one is below, so this actually stands for x0 squared minus xi. This is the usual length, this is the time difference. So this is called the space time interval such that this is invariant. That is the general definition of Lorentz transformation. And remember, this is the most general Lorentz transformation. What you might have studied are transformations in which the second coordinate system is moving with respect to the first one with a constant velocity and so on. But now this will include all transformations. It may be moving in any direction, and also the spatial coordinates may be rotated. So Lorentz transformations already include the rotations. Theory is always considered isotropic, but be extended to an isotropy in 4-dimensional spacetime, that is Lorentz transformation. Okay, that is Lorentz transformation. So now all this is a repetition. Electromagnetism in relativistic notation. Remember, this is only relativistic notation because electromagnetism as formulated by Maxwell is already consistent with relativity. So we include this antisymmetric tensor, which includes both electric and magnetic fields, in the sense that F0I is nothing but EI, electric field, and Fij is equal to epsilon ijk bk, magnetic field. So 3 components, electric field and magnetic field. There are 6 components, and remember, an antisymmetric second rank tensor in 4 dimensions has only 6 independent components, and those are the 6 independent components. So Maxwell's equations, it's better to write them again and again so that you become more familiar. Gauss law for electric field and Faraday's law of induction. Gauss law for magnetic field, right hand side is 0 because there are no free magnetic charges, and Ampere's law as modified by Maxwell by adding this displacement current term. I think there is a 1 over c in all these things, so I put c equal to 1 equal to the current. This is the sum and total of all of electromagnetism. Now I think I gave you as an exercise. So similarly, see, everything in relativistic notation should be formulated in terms of 4 vectors, 4 tensors, and so on. But this is a 3-dimensional scalar, this is a 3-dimensional vector. Both are amalgamated to consider J mu, the 4 current, which is the spatial, the time component is charge density, and spatial components are the original current. Okay, using j mu, all these equations can be written very neatly as d mu. My notation is d mu means d by dx, that is the notation. D mu f mu nu is equal to j nu. All of Maxwell's equations can be written in this compact and elegant form. So, now let us go to the Lagrangian dynamics. As I said, this is all a repetition. I do not mind repetition because for some of you who may not be very familiar, repetition always helps. The Lagrangian density I forgot to write down one more thing. I have to introduce potentials before that. So, let us introduce potentials. The 4 vector potential again. The time component is nothing but what we normally call phi 0, phi, and this spatial components. In terms of this mu, first in terms of this phi and a, the usual equations connecting the fields in terms of potentials are E equal to minus gradient of phi, the potential, electric potential, but in general if there is time dependence we have to add dA by dt. In electrostatics E equal to gradient of phi, minus gradient of phi, but in complete electrodynamics, time dependent electrodynamics, dA by dt again 1 over c can be put, and B is of course the usual thing, you know, curl A. These also can be amalgamated into just one equation, namely f mu nu, which is equal to d mu means d by dx mu, x nu minus, I am sorry, a nu minus d nu a nu. I am not giving the connections completely, but you please make the connection, show that this includes all these, show that this includes all these 4 equations. These are all good exercises for you in electromagnetism. Okay, what is the Lagrangian for this? I started writing, yeah?
This equation,
Yeah.
There is a source on the right hand side, no, J nu.
Oh, this one.
But there are 2 equations which don't have sources.
This J nu takes care of this J and rho. Yeah, what is the question?
The other 2 equations which are homogeneous,
Yeah.
that is divergence of B equal to 0 and
Yeah.
curl E plus del B by del T equal to 0.
Yeah.
Those 2 equations will not come from this one equation, right?
No, you just show, you can show that this has this zeros also automatically coming in. Please show that. See, these right hand sides are 0 in the absence of free electromagnetic charges, namely absence of magnetic monopoles. Because of that, these have to be 0. Once they are discovered, they may be discovered, because in every high energy experiment they are always searching for magnetic monopoles also. One day it may be discovered. If it is discovered, we have to change these equations also and put corresponding rho m and Jm. Until then, this remains 0. Okay?
What I am asking is that whatever equation you have written in
Yeah.
terms of relativistic notation,
Yeah,
it is 4 equations, right?
there are 4 equations, right?
So that will correspond to del dot equal to rho and these 3 vector equations for J.
Yeah,
Last equation.
yeah,
So these 4 equations are these 4 equations.
yeah.
These 2 equations.
But I claim that these zeros also are contained here. Please check that. If you just use these original definitions, these definitions, you will see that if you take del cross, E, you see del cross E is epsilon ijk, and E will be this, and then dB for epsilon ijk will come, and then you will see that they balance each other and it will give 0, and correspondingly the right hand side will be 0. I do not know right now, I cannot see it, but it is true that these are also contained in this, even with this homogeneous part also is contained here.
No, I thought we may have to define another antisymmetric tensor with electric field and magnetic field exchanging their role.
Yeah, they are the dual, they are the dual fields, yeah.
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 So then right hand side becomes 0, and if we call that as some G.
You are right, you are right. I am sorry how I missed that. So let me write down. Let me define, how do I do it? Let me define the dual of the field tilde as epsilon mu nu alpha beta f alpha beta. I am sorry I made a mistake. These are called the dual of the field. What this does is it replaces electric field by magnetic field and magnetic field by electric field with a one minus sign is there somewhere. Okay, these are called the dual field. So we have to supplement. I am sorry, I always forget this. D mu f mu nu tilde is 0. That is what you mean, right? Yeah, these 4 equations correspond to these 2 equations. I am sorry I missed that. It is good that Satya pointed that out. Okay? This is called the dual equation, and the dual equation corresponds to the homogeneous equations, and these correspond to the inhomogeneous equations with the right hand side rho and j. So I have introduced the potentials into it. So I will write the Lagrangian in terms of potential. So actually you can write it down first, f mu nu into f mu nu. Mu nu of course are always summed over. What does this mean? This means d mu a nu minus d nu a mu. Square, let me simply write square means this into itself, but with the components lowered, with the indices lowered. So that is the Lagrangian density for the Maxwell field, but in this case with the current and charge density 0, the free Maxwell field. Okay. Let us go further now. I am now going to consider a relativistic wave equation for the electron, namely the Dirac equation. One could start with non-relativistic Schrodinger equation and go to that, but non-relativistic Schrodinger equation I assume all of you know. Relativistic equation I will straight away start with, because hereafter we are going to be only in the relativistic. Everything what we are doing in quantum field theory is going to be relativistic. So we have to use Dirac equation rather than Schrodinger equation. Relativistic wave equation for electron, which is the Dirac equation. I already wrote it down. Whether the i's are there and I minus and half etc. I sometimes miss. Please correct my notes. I am not that careful. Gamma mu, which are just constants, but 4×4 constant matrices which characterize the Dirac equation. D mu is d by dx mu, minus or plus, again I do not particularly remember, into psi equal to 0. These are 4×4 matrices. They are defined just by these equations: gamma mu, anti-commutator, gamma mu plus gamma mu equal to twice of g mu nu, the same g mu nu which we already introduced. So in particular, since G is a diagonal matrix, gamma 1, gamma 2 anti-commute. Any two gamma matrices anti-commute, and the square of gamma matrices, gamma 0 squared is 1, gamma I squared is minus 1 because of the minus content here. So this is the definition of gamma matrices, and then since these are 4×4 matrices, we should regard this also as a 4×4 matrix, m 4 times, I mean m into unit matrix, and psi is a column vector. In Schrodinger equation, psi is a single component field, but for a Dirac equation, it has 4 components. It is called a Dirac spinner or Lorentz spinner, which is a generalization of the Pauli spinner which we have for spin half particle. Remember, we had a spinner, a 2-element column vector, which we used for isospin also. And this is the relativistic generalization of that. So, it has 4 components. So, this also can be, oh, I forgot to mention one thing. So, I will show it, I will write it as an exercise. Show Euler-Lagrange equation. What is Euler-Lagrange equation? It will be dl by d mu is equal to d by dx mu into dl by d of d phi dx mu. I am sorry, mu I have put here. So, something is not coming right. I am sorry, this is d phi by d. This is a differential coefficient of y phi, there is no phi there, dl. You differentiate, see L is a function of the vector potential. Actually, it is a function of vector potential, the derivative of vector potential only. So, dl, I do not know, I am making so many mistakes here. So, mu I wrote here. So, this mu I think is correct. Here I will write alpha d alpha a alpha. That is, this is a derivative with respect to a. This is a derivative with respect to the derivative of a, and then you take the derivative again. So, these indices balance and these are summed over anyway. So, this is the Euler-Lagrange equation written in terms of a. This is the only important thing. When we go to Lagrangian dynamics, it is the vector potentials which are the primary quantities, and the fields have to be derived. You cannot use fields directly in the Lagrange equation. Okay, that is clear. When we go to the charged particle interacting with an electromagnetic field, vector potentials come in the Schrodinger equation or Dirac equation. So, vector potentials are the primary objects of electromagnetism, not the fields. Please remember this, both in quantum mechanics and quantum field theory. So, show Euler-Lagrange equation leads to the free field equation, because we have not added any interaction, leads to d mu f mu nu. I write it in terms of this also equal to 0. So, these are the free Maxwell's equations with right hand side all of them 0, and that can be obtained by Euler-Lagrange equation based around the Lagrangian. Similar thing can be done for this. The Lagrangian density for the Dirac field is minus, again this minus plus etc. I am not very sure. Please repeat all these things and then derive it fully, then you will be able to correct all my mistakes. I wrote my plus here, so I should write plus here also. If this were minus, this should be minus. So, Euler-Lagrange equation here can be written for psi as well as psi bar. Psi and psi bar are considered independent fields. So, let me write down the Euler-Lagrange equation for psi bar equal to d by dx mu dl dl by d d psi bar dx mu. That is the Euler-Lagrange equation for psi bar. You can write down a similar equation for psi also. If you write it down for psi bar, you will get this equation. If you write down for psi, you will get the corresponding equation for psi bar, which is also valid. By taking Hermitian conjugate and so on, you can write down the Dirac equation for psi bar also. So, since I wrote this, so show So, this leads to Dirac equation. That is again another exercise for you. Okay. So, let us now combine the Maxwell field with the Dirac field and write down quantum electrodynamics fully. Minus 1 over 4. Let me simply write f mu nu squared, but remember this means f mu nu into f mu nu, and I had to rewrite it in terms of potentials, and then the Dirac psi bar I. Here there is a very important thing. This d mu is replaced by d mu plus I e a mu. Then only it describes correctly the electromagnetic interaction of the charged particle. Okay, the mass term. So, so this will lead to the Dirac equation, Euler-Lagrange equation. If you use this for psi or psi bar, you will get the Dirac equation d mu plus I e m. I mean the Dirac particle, the electron for instance, interacting with the electromagnetic field. Show that. So, this is also another exercise. Show that Euler-Lagrange equation for this will give you the Dirac equation in the presence of the electromagnetic field described by the vector potential a mu. So, we are now moving towards gauge theory. So, the first point to note is, if there is any question, these are all things which I think in one form or another I had already done, but I only repeated it. But if there are any questions, you can ask me. Now, we are moving towards gauge theory. The first point to note is, take this Lagrangian and apply the transformation psi x goes to psi prime x, which is equal to e power I alpha. Alpha is arbitrary real constant times psi x, constant, that is very important. If you do that, Lagrangian is invariant. L is invariant under this transformation. L prime is the same as L. That is the first point to note. Maybe I can mention one thing. Whenever there is an invariance, there is always a conservation law that is called Neuters Theorem, especially the invariance under a continuous transformation. Alpha is a continuous parameter, it can be any number, and when based on Neuters Theorem, you can prove that there is a corresponding conservation law. What is the conservation law? Neuters Theorem. This is an important theorem which will be used again and again. Neuters Theorem. If the Lagrangian density is invariant under a continuous transformation, such as this continuous transformation, there is always a conservation law. Another thing which I can mention, this is phase transformation, constant phase transformation, and phase transformation is the same. We may call it a U1 transformation. I mean, it's a unitary matrix in one dimension. because we are going to generalize this to the non-abelian SU2 and SU3. In that context, this is the simplest U1. This is U1 transformation, and it is invariant under the U1 transformation. Correspondingly, there is a conservation law. I am not going to prove it. Any field theory book will give you this, but let me simply write it down. The conservation law is the charge conservation corresponding to this invariance charge conservation. There is Q, the charge in the system. For the Dirac field, assuming psi is a charged field like electron, it is simply what is the charge? Psi bar. I have not here psi bar has come. I should have defined already here. I think I did mention it last time. Psi bar is basically the Hermitian conjugate. I hope everybody knows the what is Hermitian conjugate. Hermitian conjugate is take a matrix and take its transpose and take complex conjugate. So, here the psi itself is a column matrix. So, psi bar will be a row matrix. That is psi bar. That is, if you take the transpose of this, you will get psi 1, psi 2, psi 3, psi 4, then take complex conjugate. That is the definition of psi bar. I am sorry, that is not correct. This is psi dagger, and psi bar is multiplied by gamma 0, no, one of the gamma matrices. So, that is the definition of psi bar. Now, everything has been defined. Whether I write gamma 0 below or above is the same, only for the gamma I there will be a minus sign. Okay. So, take that psi bar and take gamma 0 psi, integrate over all space, that is charge. In general, it is a time dependent quantity, but you can prove because of this invariance that dq by dt is 0. That is the conservation law, total charge conservation. Actually, it goes much further. There is a microscopic conservation law. Define the 4 current again as psi bar gamma mu psi. Then you can show that dj mu dx mu equal to 0. Again mu repeated into the summed over. What does this mean? This means actually if you split into the time and space component, d rho by dt will be the spatial divergence of the spatial component. Let me write it like this. I hope you understand this. All these 4 components, this will come on this side, but then I have put it this way. So, this is the microscopic conservation law, namely the charge density in a region can come, actually you can see from divergences there, it can come from the surface either increasing or decreasing. So, any charge density here has to come from outside or go away from here. From this, if you integrate over space d rho d cube, you will get minus del dot j d cubed x integrated over space. Now, let us take the space all over space, all the space, all volume, in which case this will be, I mean this can always be converted into a surface integral by Gauss theorem. Namely, what is Gauss theorem? It will say J dotted with the surface element d sigma. So, consider a volume B and this is a surface S. Okay, volume enclosed by the surface. So, this can be, I have just used the Gauss theorem here, but take the surface sufficiently large where the psi and charge density, current density, everything is 0. If the surface is taken to be sufficiently large, so that this integral involves the whole volume, then since at that in that infinite surface j equal to 0, this is 0. So, that is the proof of dq by dt. This is nothing but rho d cube x. I have integrated and shown that that is time independent by using this microscopic conservation law. So, many times this itself is called the conservation law because this leads to this. Okay. All these you should be familiar with in one context or other in your MSc course, I mean that part. But the point here is the constant phase transformation, namely the U1 transformation, invariance against that transformation leads to conservation of electric charge. Now, I am going to make an important change. Instead of alpha constant, take alpha to be space time dependent. So, that psi x goes to psi prime x, which is equal to e power minus I alpha. Did I take here? I think I took plus, let us take minus everywhere. For some reason I have taken minus. Correspondingly, psi bar involves complex conjugation. So, this will be e power plus I alpha x psi bar x. Now, I rubbed off the Dirac equation, but anyway Dirac equation involves derivatives, and you can see that derivatives will act on this also. So, there is going to be complication. So, let us compute d mu psi x equal to e power minus I alpha x d mu psi minus I d mu alpha e power minus I alpha into d mu phi. I am sorry, d mu I have already written into psi. Okay, two terms are there. But we are considering Dirac equation interacting with the mu, the electromagnetic vector potential. Now, it turns out that the Lagrangian will again be invariant if, in addition to this transformation, you make what is normally called the usual electromagnetic gauge transformation. Mu goes to mu plus 1 over this alpha comes here, but with a E electric charge dV. So, let me do that simple calculation. Take IE mu, that will go to IE mu plus I, this is only 1 over E d mu alpha. So, add these two. So, you have I want to do something more to this. I have already done this, right? Yeah, I have already d mu alpha into e power. No, let me write down one more equation, please. IE mu psi multiply by psi, it does not change anything, plus I d mu alpha. When I write a derivative, it operates only on this, not on the rest of the quantities. Again, I mu e power minus I alpha, here again become minus I alpha. I am just multiplying this equation by e power minus I, yeah, I should have written that. I mean e power IE mu psi goes into this, that is I am multiplying this equation by psi, that is all I am doing, but I do not know why I am getting into so much problem. I may be making simple algebraic mistakes, please correct them. Now, add this equation to this, add, you get, add this to this, is it? No, add this, the transformation, add these two equations, transformation on d mu psi and the transformation on this mu into psi. So, the combination d mu plus I e a mu into psi transforms as, you can see the d power minus I alpha will come out. Basically this derivative term cancels, that is what we have done, we have cancelled the derivative on alpha. E power minus I alpha take out, this is a very important equation. If you simply take derivative, it has an extra term, but if you take but if you add this term, that that modified derivative is called the covariant derivative, gauge covariant derivative it is called. Covariant not in the sense of relativity, but in the sense of electromagnetism. Covariant derivative. The covariant derivative just gets a phase factor without this additional derivative term. And also you can see that under this transformation f mu nu transforms, because f mu nu is d mu nu and d nu mu. So, in that this cancels. So, f mu nu itself does not transform, remains gauge invariant. I mean that is the original gauge invariance of electromagnetism. I am just repeating that statement. We I think it was called d mu goes to d mu plus d mu chi. Chi is an arbitrary function, that is the gauge transformation. I could have discussed it in the 3-dimensional form itself, in the non-covariant form itself, how the gauge transformation works, namely the electromagnetic the magnetic field del cross A is invariant if you add to a gradient of a scalar, arbitrary scalar you take the gradient which is a vector, add it to A and then take curl of the gradient of a scalar is 0. So, because of that the magnetic field does not change under this transformation. For electric field similarly, electric field simple things which we already know is d phi by dt is I mean gradient of phi is invariant if there is a constant error, that is the simplest gauge transformation. But now with this added thing again you can see that the electric field also does not change. So, all that is contained in this statement. F mu nu itself is invariant although the vector potential changes, and hence that the full Lagrangian let me write it down, minus 1 over 4 f mu nu minus I psi bar gamma mu, the covariant derivative psi minus the mass term remains invariant. So, under this full transformation defined by this plus this together, this is called now the gauge transformation, called gauge transformation. And this is what we are going to generalize in order to construct the standard model. So, normal electromagnetic gauge invariance which you might have studied in MSc talks only about the gauge transformation of this, but correspondingly we have to make this transformation, then only the interaction term will be invariant, which is not usually not mentioned, but you have to remember that. So, under that the full thing is invariant, because now what will happen, I have written this corresponding thing you have to write down psi bar also, that will come with the e power plus I alpha. So, the e power I alpha terms cancel in this. So, although there is a derivative term occurs, if the derivative is a covariant derivative, then the covariant derivative has only a phase transformation, and for the corresponding psi bar it will be e power plus I alpha, remember. Okay. So, they cancel each other, it remains invariant, of course that is invariant, and this is invariant because I already mentioned. Okay. Because f mu nu is a 4-dimensional curl, and the 4-dimensional curl is again invariant under adding a derivative of a scalar quantity. So, let me rewrite that as a sentence because it is a very important thing. So, what we have shown is the total Lagrangian is invariant under the x dependent phase transformation. Which is what is conventionally called the Gauss transformation. Okay. Now, please note now I want to turn the table around. Turn the table around. What I mean is the following: turn the table around. Start with the Lagrangian for a free Dirac field, free electron, minus I psi bar gamma mu d mu psi minus m psi bar psi. Invariant under constant phase transformation trivially because psi and psi bar cancel each other, but not invariant under space time dependent x mu dependent x dependent phase transformation. That is clear because of this derivative term. Now, it is a philosophical point I am going to make. Suppose nature respects locality. Of course, all of quantum field theory which we have discussed are local interactions. Fields are defined at a single point, interaction also is at a single point, that way it is local. It already satisfies all the locality requirements, as you can show in advanced quantum field theory. That is one of the things which we discussed, local microscopic locality, microscopic causality it is called, locality and so on, all that is true. However, suppose we say something, demand something more, that if nature respects locality not only in letter, which is true, but in spirit also, in the sense, see, when you write down this transformation, the constant phase transformation, psi x goes to e power minus I alpha constant psi x. The electron field, let me call it electron field. Remember, I already showed you how to quantize the Dirac wave function and regard it as a field and get electrons as quanta of the electron field. So, let us call it the field. When the fields are defined at local points, but the phase transformation is a same phase transformation at all points in space and time. That in some sense is not consistent with the spirit of locality, that is what I mean. Somebody makes a phase transformation in Chennai, somebody makes it in Bombay, but the same phase transformation has to be made, then only the theory is invariant, right. That is not enough. That is why we have to make it local. Different phase transformations at different time places in space time. This is what we should demand, but we have so far demanded only this. Under this is invariant, but under this is not invariant. So, there is something lacking in the spirit of locality, and that is what electromagnetism does. That is, we introduce a vector potential and allow that vector potential also to get transformed by the derivative of alpha x suitably, as we have shown. Then the full theory is invariant under this space time dependent transformation. So, you might say that this is the justification for the electromagnetic field. So, in some sense theoretically we can derive the existence of the Faraday-Maxwell electromagnetic field, even though they might not have discovered it. Of course, this is a moot point whether theorists are that clever, but now at least looking back, this is true. Even if electromagnetism had not been discovered, by demanding that quantum field theory respects locality in spirit, we could have derived all of electromagnetism. Okay. So, Maxwell's electrodynamics can be derived, that is what I mean. Because once you add mu, then we have to have dynamics for mu. So, you add f mu nu into f mu nu, which is also invariant under this transformation. So, the full Lagrangian can be derived just based on this argument. So, let me say that that is what I mean by this. Maxwell's electrodynamics can be derived from the demand, if we demand that nature respects locality of interactions, locality of the whole theory in later, that is already true, but in spirit also, in later as well as in spirit. So, there is some philosophy involved in this. Okay. So, any questions so far?
So, in classical electrodynamics,
Yeah.
we always say that, okay, let us consider a situation where the field is 0.
Yeah.
Well, we have no field,
Yeah.
we have a particle.
Yeah.
So, such a case, like what you've shown, if you take a Dirac equation
without electromagnetic field, yeah.
Without electromagnetic field,
yeah.
then it will not be invariant under this local.
Yeah, it will not be invariant. Yeah.
So this means that you cannot have a situation where we can set field equal to 0. Field is always there.
Field is always there. Only thing is, in some places the field may happen to be 0. That's all. More generally, field is there. Once you go to quantum field theory, you will see that vacuum fields exist all the time and at all space. Vacuum fluctuations exist. So you cannot ignore electromagnetic field, although you might not switch down your power. You might not have switched on your power, so then no electric current, no electric field or magnetic field may be there in your room, but it is there hidden already.
No, my question is this requirement of local phase invariance, phase transitional invariance.
Yeah.
Does it tell us that field is always there? Means there is a vacuum field which we have to.
Yeah. See, this Lagrangian exists whether the actual field is 0 or not. Whether the actual field exists or not, the full dynamics has the fields in the Lagrangian. Because if the Lagrangian does not have it, we cannot bring it back again. So, since a more general situation includes the fields, the Lagrangian at least will have it. Whether in a see, we have to distinguish between the general Lagrangian and the actual state of the system, which may be momentary. One moment it may not be there, next moment the fields might come. Because we know that the possibility of fields existing is always there, but we might in an artificial way make it 0. Okay. Now I am going to generalize. I am going to generalize this simple phase transformation, what we called U1, to non-abelian groups like SU2 and SU3. That is the next important.
This x-dependent thing we call this U1, right? U1.
Yeah,
U1.
that also is U1, but that is I want to introduce a general notation which I introduced long ago, but nobody has picked up. See, there is Lorentz transformation, normal Lorentz transformation, where the Lorentz transformation matrix mu nu is constant, depends only on velocity and so on. then Einstein generalized it to the general theory of relativity, where instead of constant Lorentz transformation on the coordinates, space-time coordinates, any arbitrary space-time dependent coordinate, that is general coordinate transformation, arbitrary general coordinate transformation. That is what created general theory relativity, which included accelerations and gravitation also. Okay. In the same way, e power I alpha transformation with alpha constant, I would call it special U1 transformation, and e power I alpha x transformation with x alpha x arbitrary is general U1 transformation. I think this is a very good terminology. Although in books one is called the global transformation, the other is called the local transformation, all those things are there. But following the terminology used in relativity theory, the special theory relativity and the general theory relativity, here we can introduce special invariance and general invariance. Okay. So now I am going to generalize the U1 to SU2 and SU3. I mean any arbitrary group. Although most of the time I will be using either SU2 or SU3, but you should be able to rewrite them in general language. So what we have done so far, you can say abelian gauge theory, because U1 is an abelian group, namely e power I alpha 1. Let us consider the special U1 transformation, e power I alpha 1 transformation, and then apply e power I alpha 2, they commute. Abelian. So this is an abelian U1 group. Abelian group. So this is U1, but it is abelian. So we replace them by matrices. That's all we do to get to the non-abelian. Non-abelian. That is what Yang and Mills first did. It's called Yang-Mills theory. So for simplest example is again SU2. Consider an object, a particle which exists in two forms. It may be proton neutron for SU2 or U quark and D quark. So let us call them psi 1, psi 2. Use a general notation. So what is the transformation? Psi prime is equal to e power I alpha I. Straight away I will go to the space time dependent things. Alpha I x into tau I by 2 into psi. These are three real arbitrary functions of space time, and taus are Pauli matrices, 2 by 2 Pauli matrices, which satisfy the commutation relations and the anti-commutation relations, which we are already familiar with. And to make it more general, let us write it as simply a unitary transformation. So whatever I am doing, although it is only 2-dimensional and this is 2-dimensional matrices, so this U is a 2-dimensional matrix, we can immediately generalize to 3-dimensional, that will be SU3, or n-dimensional, in which case it will be SUN. Okay. So if you use this notation, psi prime is equal to U psi, thereafter we will use this notation. This is the transformation. Remember all these adjectives. Unitary means U dagger U equal to 1, unimodular means determinant 1. That means in the exponent the trace of these has to be 0. All these we have discussed. So
You have written psi 1, psi 2 column vector.
Yeah.
Each one of them is a Dirac.
Each one of them is a 4-element Dirac spinner. Yes, correct. or it may be psi may be a scalar field. We will soon come to scalar fields where it will be only scalar fields, okay. That also is possible, but let us consider because I am going to consider only Dirac field right now. Later we will have to go to scalar fields before bringing in spontaneous breakdown of symmetry and Higgs mechanism and so on. So now some simple algebra is involved. So do that algebra. If you take d mu minus I g, g is a real constant. It replaces the E which we had in the electromagnetism into tau I by 2. I is repeated, so it is summed over. This sometimes we will write it in this compact notation, alpha vector dot tau, vector in isospin space. Okay, here I continue the same notation, tau I, introduce just as in U1 theory we introduced one vector potential A mu. Here there are 3 elements here. These are generators, 3 generators, and so we have to introduce 3 vector fields. Instead of one vector field A mu, we have 3 vector fields. So introduce W mu I going from 1 to 3. So you remember this is the analog of A mu which we introduced for U1, A mu analog of A mu for U1. So again sum over I. So in the Dirac equation which describes the dynamics of the psi, there will be derivative. Those derivatives have to be replaced by this gauge covariant derivatives, because then when you make the transformation, correspondingly you have to make a transformation on W mu. So once you make this, make the transformation W mu, already I have changed the notation. This quantity sort of thing which will come always take the vector fields which are going to be called gauge fields, because mu is a gauge field, right. It is not the f mu nu, but since there is gauge invariance, mu is always called the gauge field, and this is a generalization of the gauge field. So this gauge field there are 4 of them, I mean 4 components. So there are actually 12 of them, because in SU2 case there are 12 of them, but if you multiply them, this will be a matrix, and that matrix I will call W mu hereafter. So W mu hereafter just denotes, I think I have already included, divided by 2 also. Take the W mu I, multiply by tau I, sum over I, and divide by 2, and that is called the gauge fields, 4 of them, but written in matrix notation. Instead of writing as 3 components, it is a matrix notation. So I am going to write down the gauge transformation. See now what is the idea? When we wanted to construct a Lagrangian which is invariant under the gauge transformation, we had to not only transform the size, but mu also changes by the derivative term. Corresponding thing I have to write down for the non-abelian case, which is a little bit more complicated. The transformation is this. Instead of 1 over E, we have to have 1 over G, and then this will be a derivative term, but modified this way. This looks more complicated, but this is a transformation. So whenever psi is transformed by this unitary matrix to psi prime, W, the vector potentials, have to be transformed, but remember they are matrices and U is that same unitary matrix. Now you can see how this includes the old U1 transformation. In that case, W mu is not a matrix, it is simply a number, and so they all commute with each other. So U into U inverse 1, e power I alpha, e power minus I alpha commute with 1, and yeah, here what will happen when you differentiate it? D mu alpha will come, e power minus alpha will come, e power, I think this is one of them is minus, e power minus I alpha will come, e power plus I alpha will come, they will cancel each other, only the d mu alpha will remain. So, d mu alpha divided by u corresponding to the u1 transformation is a special case of this. So, more generally when u's are matrices and w's are matrices, this is the transformation of the vector potential. Whenever the u1 transformation, I mean the SU2 transformation or SUN transformation on the Dirac field is applied, correspondingly the vector potentials have to be transformed. Just as whenever we applied the space-time dependent phase transformation on the electron wave function psi, we transformed the mu also by mu going to mu minus 1 over e d mu alpha. The same thing I am saying, whenever you make the transformation, transform this also. Now we can write down the Lagrangian. So, let me just write down that Lagrangian and then we can have a break. Correspondingly, now I am going to introduce another quantity. Remember, in electromagnetic case, apart from mu, f mu nu also comes, right, in the Lagrangian. Actually, it is f mu nu into f mu nu which comes in the Lagrangian. Correspondingly, there is a g mu nu. So, let me introduce g mu nu. You can say that these are the fields derivable from that potential. So, it will involve derivatives d mu. Remember, W's are the matrices, n by n matrices. So, this also is a matrix, but in the case of u1 this was enough, but in this case this is not enough. We have to add minus Ig, the commutator of these two matrices. This is a very important term, a quadratic term. So, that is the generalization of the electromagnetic field f mu nu for the Yang-Mills case. Next, we can prove that when W mu transforms like this, using this, G mu nu, how does it transform? G mu nu transforms in a very simple way, basically. That is the reason why G mu nu is introduced. Here again, the analogy with the electromagnetism breaks down. In the electromagnetism, remember, under the Gauss transformation, f mu nu did not transform, but here it does transform. The derivative term is not there, but this term is there. So, this involves some algebra to be proved. So, I will prove it when I come back to be proved. If we prove it, then the Lagrangian of the Yang-Mills theory is completely written now on the basis of whatever I have said. This is a covariant derivative minus m into psi minus 1 over 4 trace of G mu nu G mu nu. Instead of the old form for electromagnetism minus 1 over 4 f mu nu, here trace of the matrix has to be, because Lagrangian itself cannot be matrix. So, that is all. That is the Lagrangian of the Yang-Mills theory. For instance, for SU2, psi will interact with the triplet of the gauge bosons. The quanta of the W fields will be triplet now for SU2. For SU3, it will be octet, because it will be always the number of generators. Remember, in SU3 the number of generators are 8, so 8 gauge bosons. So, the way we have written down, once we introduce this notation with U an n by n matrix, then it takes care of all the groups at one step. So, this is the Yang-Mills Lagrangian in parallel with the QED Lagrangian, namely Maxwell Lagrangian. You can say is equal to psi bar I gamma mu d mu minus Ig a mu minus m psi minus 1 over 4 f mu nu. So, the analogy is very clear. Okay. So, I think we will stop now. I will come back after a break. Maybe I will come back by 11:45. Then you can ask questions. Unless you want to ask questions now, you can ask questions now also, or after I come back. So, first 10 minutes, 15 minutes, we will take up the questions, and then I will first prove it. First prove that thing to be proved, G prime, how it is related to this. U inverse can be written as U dagger also. Remember, U's are all unitary matrices. So, this by multiplying by U dagger inverse or something like that, you can see that U inverse is nothing but U dagger. For unitary matrix, that is always true. So, this requires some work, some algebra, which has to be done carefully, because so many indices come, it might confuse you. So, I will try to do it carefully on the blackboard, and then we take up the further development of non-abelian gauge theory. Okay.
Okay, we will make that 11 times.
Yeah.